Hello.
Hola. Okay, good morning, guys. The next speaker is a Professor Hedibert Lopes. He obtained the PhD degree in statistical and design science from Duke University from 1996 to 2004. He was assistant professor and associate professor from Departmental of Statistics and Method from Federal University of Rio de Janeiro. Became associate professor of econometrics and statistics at the University of Chicago School of Business in 2007. And currently he is a full professor of statistics and econometrics at Insper, that is Instituto de Ensino y Pesquisa. He has been working on different areas in statistics and econometrics, for instance, based on abordaging in dynamic models, factorial models, statistics of extremes, dynamic couple, models mix, and this presentation, he talking about efficient sampling for Gaussian linear regression with arbitrary priorities. Let's thanks to Hedibert.
Okay. First of all, I would like to thank Paulo and the organizing scientific committee for inviting me to visit the Federal University of Bahia. I have been to Salvador a few times, but never visited the university, even though it's so close to all the places I've been. I also want to say that this is joint work with Richard, who was in Chicago advising Jing Yu He while he was a master's student in statistics, and then he moved to a PhD at the Chicago Booth Econometrics and Statistics PhD. And now Richard is in Arizona, and now I'm back in São Paulo. So the story of this paper is essentially computational. So we wanted to develop a faster, more efficient way of dealing with a very standard problem, the Gaussian linear regression problem, because it's well known. And the reason why we want to talk about this particular class of model is that, as you're going to see in the next few slides, you can actually rewrite most of the regularization literature as a Bayesian approach, finding the mode of the posterior distribution for parameters for different types of priors. So I'm going to do like a brief review of that literature to set the stage, and then I will spend some time talking about how we take advantage of the Gaussianity of the linear regression to make a proposal for sampling the parameters of this model faster and more efficiently. And hopefully I'll show a few simulations to show that that's the case. Okay. So the motivation is run a Gaussian linear regression and a new prior. So each one of us here could have a different prior, and the natural order of things would be you do the math, try to write a new Gibbs sampler, like Lily and I were talking about outside the room a few minutes ago. You have a new problem, then you have to design a fast MCMC scheme. These days you have to do parallel computing. You have to mix R and C++ or Python, whatever is faster to run the different parts of the code. That's what you do. And then someone else comes with a different prior, and then says, oh my God, now I have to do the whole thing again with a different type of computation. So it becomes very time-consuming and always customized. As I say here, maybe it's hard or easy to find full conditionals. Probably might require data augmentation, lots of expertise, latent variables. So this is like the day-to-day work of a Bayesian computation, applied Bayesian that needs computation for posterior inference. So what we do here is we take advantage of, as I said, the Gaussian likelihood. And the fact that we have a Gaussian likelihood would make us, eventually you'll see it, we go from sampling, think about a regression with 300 regressors. So instead of finding a Gibbs sampler for 300 coefficients, we're going to use a Gibbs sampler that has lots of interesting, easy to sample full conditionals, and one which is univariate in an interval between 0 and 2 pi. So everything boils down to being able to sample from that weird but univariate and limited random variable. So it's a very strong result, easy to prove. But all remains as it's all based on the Gaussian property of the likelihood. So here's what I'm intending to do, is to briefly discuss, famous regression strategies like the ridge regression, the lasso regression, and a few other types of shrinkage priors. Then I will talk about the algorithms that we developed in these 2 points here. And if I do have time, I'll talk about the simulations we performed. And the interesting thing that I hope I will have time to talk about is that everything we did in this project is packaged in this R package base LM. So if you know R, LM is the R function for linear model. So now and there are several other Bayesian packages for linear models. So we called ours just the base LM. If you're familiar with the Bayesian literature on quantitative marketing, you know that Peter Rossi, Rob McCulloch, and Greg Allenby, they wrote like a bunch of code for their marketing, applied marketing book. And they also have packages there, but not for this kind of problems that we want to tackle here. If you have questions, you can stop me through my presentation. It's probably easier and better, more interesting. So I will do like Elizabeth did yesterday, so I'm going to move around here. So you can look at people on this side now. So a brief review of the Bayesian regularization. So forget about this name Bayesian right now, and just think about this slide as a replication of a slide someone presented yesterday. I mean, I saw in the morning, someone gave a talk here in a session, and he had one slide that was pretty much like this. So we have a standard linear regression, and if you're not Bayesian, you just and if the X matrix has some nice properties, you just take beta hat as the OLS estimate. X transpose X to the -1, X transpose Y, and something similar to sigma squared. X is the main object here, so forget about sigma, it doesn't matter right now. However, sometimes you want to penalize, the columns of the matrix X. You might have not only multicollinearity, but you might have redundancies in many different ways. So you might have 2 variables and the third one is irrelevant. So what this ridge regression is trying to do, it comes from many different directions, but one direction is to say, I want to minimize the sum of the square of the residuals, which is the OLS, but I want to penalize that if I include a variable, but the coefficient in that variable is not too important, I pay a value which is proportional to this lambda. So according to a positive penalty, in this case the quadratic penalty. The effect of including that lambda is essentially to say, well, now my X transpose X to the -1 X transpose Y is a little bit inflated by that lambda. So I take this X transpose X, which might become ill-conditioned, it might have near multicollinearity. But then if lambda is large enough, then I avoid that multicollinearity. So that could be also a computational solution, not necessarily a modeling solution. Okay. And the reason why I present here the ridge regression before the lasso regression is because it looks like an unnatural extension to, instead of penalizing according to a L2 norm, I can penalize according to an L0 norm. But the L0 norm is very painful. This L0 norm means I include or not a variable. It's like a 0-1 penalty. So if I have P equals 100 variables, I have 2 to the power of P possibilities. So it's always, I mean, everyone that does model selection knows that traversing the space of 2 to the power of P models is very difficult, sometimes impossible, depending on the size of P. If P is 100, 2 to the power of 100 is what? I don't know. There is one of these numbers that is more than the atoms of the universe, 2 to something. But the L1 norm is not too complicated. It's appealing because there are very, very fast, intelligent algorithms to find this beta lasso estimator. And the idea is that you penalize the same way that you penalize using the ridge regression. The difference is that with the L1 norm, the mode of the posterior, of the mode of the likelihood might be found in an edge, in the corner of the parameter space, which means that, you know, with probability 1, one of the coefficients or several of them will be exactly equal to 0 at the mode. Not necessarily, you know, the variance is another story, but the mode might be like at 0. So let me show you the picture. This is the picture. Think about two coefficients, beta 1 and beta 2. When we talk about the ridge regression, we are basically saying we have a circle, bivariate normal. So think about a bivariate normal. When we do talk about the lasso penalty, we are talking about this diamond here in the middle. So you have like, if you fall, for whatever reason you fall in that edge, or that one, and that one of these two coefficients is 0. Therefore, you kind of force the coefficient to go to 0. So going back here, both methods are performing what we call shrinkage. So we have coefficients that are floating around beta space, and here is 0. So all of them are like making these guys closer, a little bit closer to 0. But only the second one has the possibility of making some of them actually 0 at the moment. Not the ridge regression. So here you have shrinkage. Here you have shrinkage and selection. So that's the idea. Like, it's a very nice idea because you go from a 2 to the power of P model, you have to rank all the 2 to the power of P possible models, to a solution that eventually says, well, depending on how big this penalty is, a fraction of the coefficients will be 0 and the other ones are not going to be 0. So I made a model selection. So that's why the name lasso. The SS is for shrinkage and the other S is for selection. The O is for operator and the LA is the least angle, which is the algorithm that is down here to find the mode. So the least angle, shrinkage, selection operator. So those are two possible penalties that we aggregate to the Gaussian linear model. So this slide is basically to say, to try to convince you that, okay, this is what lots of people in machine learning do when they talk about penalizing or regularized regression. So even though they might not use this first line, because they don't want to say that it's Bayesian, or sorry, it's likelihood based. And if I do say, if I give you, as a machine learner, I give you this objective function that is minimizing that, you can definitely say, well, you know, take the exponent of this minus, it becomes like the kernel of a multivariate normal. Oh, if that is the kernel of a multivariate normal, this is the kernel of a prior, and this one. So here's where we bring the Bayesian terminology to the table. In all these priors, we have, you know, conditionally on some variance component, a mixing distribution with a Gaussian center that's 0. So if I take the argument that maximizes in beta this product, or in this case, the log of the prior, or the likelihood, and the log of the prior, we're essentially penalizing the log likelihood with a penalty that is equal to the log of prior, if I keep this C fixed. So if you look at that for a second, this expression, that is exactly of this kind. Same thing. So from now on, I'm going to assume that I convinced you that this is basically a Gaussian linear model with a penalty that looks like a prior. So now I go to say, well, what kinds of priors for beta given psi is always Gaussian, but what about the prior for psi? So depending on how you pick this prior for this variance component, you have shapes for the prior of beta that are different. So here are the two previous ones. So it's always of this format, a scale mixture of Gaussians. So the distribution of beta is centered around 0 with a variance psi. Depending on how I mix that variance, the prior marginal for beta, if this distribution here for psi is an inverse gamma, the marginal for beta is a student t. If that distribution is the exponential for psi here being like lambda squared, then I have what we call the Laplace distribution, also known as double exponential distribution, which is the lasso solution. That's why I call here lasso. Someone else, proposed like 10 years ago this NG prior. The N is for this Gaussian, and the G is because we are using, instead of an inverse gamma, you're using a gamma for this coefficient C. When you do that, the actual distribution of beta is not student T, it's not Laplace, it's not normal, it's normal gamma. It's another distribution, which looks like normal, looks like gamma, but it's not normal, it's not gamma. It's this one. And finally, if I take this variance, take the standard deviation of the prior for beta, and say that standard deviation has a Cauchy tail. So if you remember, the Cauchy is a t-distribution with 1 degree of freedom. It's the one that has no mean and no variance. So if you draw a picture of the Cauchy distribution, it goes like this, and then it goes like that. So what this is saying is that just take this Cauchy 0, 1 to the positive side, and then just flip it over to the other side. So it becomes like a distribution that goes like this, and then it goes like that. I'll show you a picture in a minute. So 2 additional priors with the same prior for beta given C, and again, going back here, with the same Gaussian, the linear Gaussian model. So here are the 4 marginal, 5 marginal densities for beta, depending on which regularization you're using, which regularizing prior or penalty you are using. So it's hard to see what's happening with all of them in the tails, but here in the middle, even if you are in the back of the room, you could see that the ridge looks like a normal distribution. So there is no place here in this distribution that concentrates around 0. It is concentrated around 0. All of them are producing shrinkage, as you can see, but only the ones with this corner are the ones that produce possible zeros in the posterior mode. Yes?
I think I was wondering if you'd rather use degenerate distribution. Would you recover the regular linear regression without shrinkage?
When you say the generated distribution, you mean I put a point mass at 0 for each coefficient beta and a known point mass for the rest?
Not for C.
For?
The other parameter.
So if I have a distribution for psi that collapses in a point, then the distribution of beta is normal. So this integral will be just like a normal centered around 0 with a fixed value for psi.
Then you have a
You mean regular in the sense that you're doing a Bayesian update with a prior for beta which is centered around 0 with a scale of like 3.7, for instance. Yeah. There's nothing wrong with that. So what he suggests is that the trivial, naive solution will be like a line 0 here before this 4 that says, well, just fix that point coefficient in a number that you like. Usually, if you ever done a Bayesian regression, and without this, additional regularization, shrinkage properties, you would basically say, well, I don't know these parameters, I'm going to center them around 0, the betas, and I'm going to say that the variance is like 100 for all of them. So that prior is Gaussian, the likelihood is Gaussian, the posterior is closed form Gaussian. We're happy, we are promoting shrinkage because any Bayesian estimator is a shrinkage estimator, biased. But here, we are basically saying, well, let's play a little bit more with that. So let's put another layer of priors on the variance component. And apparently, what you said is basically the black one. It will be just like that as well. If you think about the normal gamma is the magenta, whatever this color is. And the horseshoe is, I can explain the name later, is the blue one. So it's hard to see what's happening with the density in that picture, but it's easier to see what happens to the log of the density. So the log of the density tells me how fast the tails are going to 0. So in the Gaussian prior, which means the ridge regression, the tails are falling to 0 very closely. In other words, if you use the Gaussian prior, purely Gaussian, you are promoting a lot of shrinkage in the coefficients. In other words, any coefficient that should have been below -5 or above 5 will be shrunk to that interval. So those that are very close to 0 will be shrunk to 0, but the ones that are far away from 0, they're also going to be sunk towards or moved towards 0 with this regression. You see that all the other ones, they are trying to avoid that. So they make the tails fatter. The one that makes the tail fattest is the horseshoe, because of the Cauchy tail of the half Cauchy distribution. But that is one property. You want to shrink, but you don't want to overshrink. And here in the middle is what you have like a black hole. Everything that is near 0 is going to be sucked to 0 if we use the horseshoe or the normal gamma prior, or even the Laplace, because it has like a little edge there. So you see what's happening here. I haven't even started talking about the computational aspect of this. What I'm trying to see, or what I'm trying to do is to show you, at least with this brief review, that nowadays, maybe 5 years from now, this will be irrelevant, but nowadays, a lot of people are using regularized regressions to pick which variables are important in linear Gaussian regressions. If you go from the linear Gaussian to a logistic regression or to a mixed generalized model, this won't work, because what I'm going to present here is only valid so far as long as I have in the first layer the normal distribution for the errors of a linear regression. And my hope is that now we can see that we can play around with this prior for psi, and that will lead to priors for beta that promotes more or less shrinkage and selection, depending on which one of the priors you do. But the point is, if each one of us pick one of these priors, now each one of us will have a nightmare of designing a posterior simulator for each case. And if someone comes tomorrow and says, well, you know what I'm going to do for my master thesis is I'm going to make a prior that mixes these 4 priors. Then you're going to have to combine all these MCMC schemes the same way. What we are saying here is that, no, you don't need to do that. Whatever prior you use for beta, if it's one of these 4, if it's a combination of these 4, anything, as long as I can evaluate the densities pointwise, I can sample using just one method, assuming that the Gaussian likelihood is available to us. So now I'm gonna dive into the how we solve this problem. So can I write here on this board? So in general, if you remember the model, we have a Gaussian likelihood, y given x and beta. Forget about sigma square. Well, let's keep sigma square here. This is normal. X, beta, sigma square identity order n. We have this prior for beta given c. We have a prior for c. And now what I want is to talk about the possible distribution for beta, sigma square, c, given the data and the x. So that's what we want to do. In general, we have like full conditionals for sigma square given beta, c, y, and x. For c given beta, sigma square, y, and x. These are usually easy. Piece of cake. The hard one is getting to sample the whole vector of beta given c, sigma square, y, and x. So that's where we concentrate our effort. So whatever you do here, fine, pick whatever you want. Then we need to do, but remember, we're thinking about this as p dimensional, where p is, let's say, 100, 300, 500, or 1,000. And n, the sample size, could be like 1,000, but it could also be 100, or 500. So in our simulation, we have a case where n is like 100 and p is 1,000. We have way more variables than we have observations. So if you design your Gibbs sampler or your customized MCMC, these are easy. You can get like univariate full conditionals for these various components. But now conditional on everything, how do I sample from this distribution? Remember, beta now is a vector of dimension 1,000. Think about that as the goal. So the idea, I'm going to go straight here to the algorithm and explain a little bit of it. The idea is, think about this delta as our beta. I kept the notation for delta and I'll explain later. I could have written as beta directly, but think about that delta as my beta. Okay? So the Poisson distribution for beta, conditional on everything else, so this will be like the full conditional for beta, has a Gaussian component and something that I know how to evaluate pointwise, my prior, but I don't know how to sample from that. So a Gaussian for beta centered around 0, and here is the variance, V, could be like the diagonal matrix with that psi's, and a likelihood, and a prior. I just changed the notation here to keep it with the original paper. But the most important message here is the Poisson distribution is the product of a Gaussian term and something else that I can evaluate pointwise. Any question? Like, someone starts speaking. Was it like my friend from Waze? Because she likes to talk to me every now and then on my phone as well. Okay, so if this is more or less clear, now it comes some tricks, very simple tricks from computational statistics, class that we learned as an undergraduate student, that basically says if 2 variables or 3 variables, V0, V1, and V2, are all normal 0, V, which is just like this, and I have a constant theta in the interval 0, 2 pi, like an angle, we can always take the V0 and V1, this should be 1, sorry. I can take this V0 and V1, any linear combination of Gaussian is Gaussian, so we know that. This is zero mean, that's zero mean. It doesn't matter what this quantity and that quantity is. The mean is also zero, so it just remains what? The variance. But the variance of the sum, because they are independent, is the sum of the variances. And the variance of the first one is V0 times the sine square. The variance of the second one is V times the cosine square. Well, V is common to the two components, so it will be V times sine square plus cosine square, which is 1. So the variance of this quantity is also that. So why would I care about this? And here's where, as a data augmentation person, we look at that and say, well, if I think about one of these V's as my previous value for beta, and I just draw another V, construct that sigma, that delta, I could use this result to update this beta coefficient. But then someone said, oh yeah, but how about the theta? Because you need that. You cannot just stick a particular value of theta. So when we do parameter expansion, we can do that. So anytime you have a likelihood that when you expand that likelihood to include some latent variables, it makes the likelihood breakable in terms of it's easier to sample from that more augmented likelihood. You should take advantage of that because you take a very intractable likelihood, now you break it in two parts, but then a very simple MCMC theorem says that if you included a latent variable and you keep sampling that latent variable and throw it away, you're actually sampling from the part that you care. You just ignore the rest. So you expand the parameter space to be able to use standard techniques, but then you throw everything that was only there to facilitate your computation. And I'm going to explain that in detail in here. The only thing I care is this one on the top, P of delta. But P of delta is the integral of this joint with respect to V0, V1, and theta. So if you gave me a joint distribution with more variables than I need, but I only need one of them, I only have to integrate out with respect to everything else, and I get the marginal of delta. But how we that do Monte Carlo simulation integrate out things? What is the strategy we use to integrate things out? Well, you sample a bunch of these other guys to be able to sample jointly everything and throw away everything. So I'm going to sample V0, V1, theta, and delta, jointly. But then I'm going to throw away all these V0s, V1s, and delta at the end of the day. Then you say, okay, fine. You just have the joint as whatever was the density that you had initially, the Gaussian with that variance, and now the non-Gaussian part, which is in our case the prior, evaluated at this point. Remember, V0 and V1 are very long vectors that mimic the behavior of beta. So like 1,000-dimensional vector V1 times a number, the sine of theta, plus 1,000-dimension vector V1 plus the cosine of theta. So that becomes the evaluating the prior at that new point. So now I need to sample from this I would call that 4-dimensional joint. This is scalar, that is scalar, that's scalar, that is a 100-dimensional vector. But think about these 4 components. What we do is we break these 4 into full conditionals. V0, V1 given the rest, delta and theta given V0 and V1. The notation is wrong here. So if I flip through these two, at the end of the day, I can simply throw away the other quantities. And it's very easy. And that's where the Gaussianity plays a very important role. It's very easy to sample from this joint by sampling some V from a multivariate normal, that multivariate normal that we have at hand. Then you evaluate V0 and V1. With that, you just obtain V0 and V1 as a function of delta and sigma, and that indirect value of V. So if you work backwards, you'll see that you reconstruct the delta and the theta as you had before. So Easy to sample from a multivariate normal of dimension 100, easy to do that in R. Evaluate pointwise these two vectors. Remember, this is a vector of dimension 100. This is also a vector of dimension 100. Fine. Well, how about the other full conditional? Well, once I'm able to sample that theta, remember that number between 0 and 2 pi, once I'm able to sample that, I can just plug that in here, take the V0 and V1 that I augmented to make my life easy, then I can just construct delta deterministically, conditional on the other two. That guarantees that these draws of delta, they come from the posterior distribution of delta. So, easy step, I don't know yet, easy step. But there are 4 steps here to produce draws from delta, which is the 3rd line of our MCMC here. Okay. So the only thing that remains is this step in magenta. So what is that step doing? It's sampling a scalar random variable between 0 and 2 pi. So any method that you use, it would work fine. So that's why the elliptical slice sampler is used, because we're going to sample this one distribution by, slice sampling. But it's univariate. So slice sampling in the univariate case is always better in general than Metropolis Hastings and other alternatives. But the key, in order to get to that point, I had to use the Gaussianity of the likelihood to construct my sampler. So working backwards. So if I have a very large likelihood, which is non-Gaussian, and a prior, which is one of those 4 or 5 that I presented, when we got to this point, easy, when we got to this point, I could not use any of these results. Because that result, that key idea, comes from Gaussianity. So that's the price. But we claim that this is still a very large class of models that people are using nowadays. Maybe they won't use it later. That's another issue. So someone else will have to invent other methods for those more elaborated models for regularization, Bayesian and non-Bayesian. This is true. I knew that was going to be very small, so I made the picture. Well, let me go back. I'm going to explain heuristically, through pictures, how we do that. Someone just lost a speaker. How are we going to sample from this univariate distribution? And this is just for those who don't know exactly what the slice sampler is. If you know, you're going to find this in the next 2 minutes very boring. How much time I have? 20 minutes? Okay. But I'll try to finish before that. So I'm going to explain to you. Remember, that theta coefficient is between 0 and 2 pi. So it's just theta. And this one in red is the theta that I have in the previous step of my MCMC. So let me go back to that slide. So when I start here, I have V0 at time I minus 1, V1 at time I minus 1, delta at I minus 1, and theta at I minus 1, where I are the sequence of MCMC draws. So if you have done that before, you know. If you haven't, then you're probably already lost here. So how do I sample from this distribution that has a format that I don't know? I only know how to evaluate this density. Someone could use like a random walk metropolis, any sort of uniform. You could sample from a uniform and pick a draw that has the ratio of probability that is as high as possible. The slice sampling essentially says, well, you sample a new draw, which I call here theta tilde, from the interval 0 to pi. If that draw leads to a height or a density lower than the one where you're sitting at in the last step, and you say, well, this was not good enough, so I'm going to move that A to here. So I move that A to right there. So now I don't have theta vary from 0 to 2 pi. I have theta vary from A to 2 pi, where A is this guy that I simulated. I draw here like the length of this interval, you know, in my piece of paper is like 4.25 centimeters. So you can see now it's 2.5. So I narrowed the interval of variability. So I sample another one, another theta, in the interval A, which is this one, and 2 pi, B. I draw that guy, again, that's smaller than that one, but that is above that value theta j minus 1, so I move B to here. So you can see that I keep moving A closer to the existing draw and B closer to the existing draw. In the limit, I'm going to collapse very near and then I'll draw something in that region and I'll accept it. So in the third step, you see that now the interval is from here to here, so we jumped from 0 to this quantity, you jump down from 2 pi to that quantity. Now that I draw something that has a higher likelihood, then I make my new theta, you see theta j, that value, and I move my chain. So and that is done at each single step of my MCMC. The only price we pay is that we are sampling a univariate component. Okay. So here's the most important algorithm of this slide, of this presentation. Where did you press here for magnifying? Which one? Zoom. Then I'll zoom out. All right. Then I'll zoom out. So you see what I'm doing here. So we're sitting on a step like this here on the board. I draw this V from that Gaussian distribution. V0 and V1, I force it to be these quantities. Remember, I do have delta and theta from the previous step. Now, what I do is I draw quantity from that uniform between 0 and then 2 pi, which is we're trying to replicate this height. Oops, sorry. Here, and then I initialize A and B at 0 and 2 pi, and I cycle through this step. So this whole step 2 is basically sampling a univariate quantity theta. At the end of the day, I compute the delta, and now you see why I had this delta, because delta, what I called here was beta minus beta hat, OLS, whatever, and then I can construct beta going backwards, beta hat plus delta, if I want to keep the original parameterization. So it looks like a complicated method, but it isn't. It's very simple. So this was like a more visualization to show the same thing that I did by hand. I like my handwriting better than this, so I'm going to skip this. So let's see. Here, okay. What we call this sliced within Gibbs is that the way we have beta as a very long vector of coefficients, you can still do the same kind of computation by breaking beta in blocks. You don't have to sample the whole vector of beta jointly. Because we already made all the computation based on a particular theta, unit scalar theta, if I break, let's say that beta has 1,000 coefficients. So if I break it in 10 groups of 100, for each one of those 100, I have one theta, I update that beta, use that beta updated to the next block of beta with another theta. So I break into Gibbs sampling full conditionals, but in each one of them I need a different theta. So it's not computationally expensive. And why would we want to do that? Because we all know that sampling vectors of lower dimension is usually more efficient than sampling joint big vectors. Even though just sampling joint will lead, in a way, to the proper distribution because you're taking into consideration all the covariance structure, it's very easy to, in a vector of dimension 1,000, any small variation might be like very far away from the existing vector because it's pretty hard to think about in 1,000 dimension. So when we do this variation, we can actually use another trick, and this also makes our computation very efficient. And that's why you need to study a lot of statistics, not only data science. Because if you study statistics, you know what sufficient statistics are. And we know that if I have that Gaussian distribution for y given x, think about that equation here on the board. Y given x beta, forget about sigma. So do you need all the y's and all the x's to learn about beta from the likelihood? No, because when I write the likelihood, so let's write the likelihood together here. I think I'm going to write here on the other side. If I don't fall. When I write the likelihood of y given beta and x, sigma squared is given. This is proportional to the exponential of minus 1/2 y minus x beta transpose y minus x beta. Okay? That's the multivariate normal. When you write that, you expand this. This is equal to the exponential of minus 1/2 y transpose y minus 2 times beta transpose x transpose y plus beta transpose x beta. Okay? I just, I expanded the square. Well, when I completed the square like that, I only need y times y. So y is n by 1, so this is 1 by n, and this is n by 1, so this is a 1 by 1. So I need that value. Sorry. I also need x transpose y. Well, this is p by n. This is n by 1, so this is p by 1. So I have here one coefficient, I have p quantities here. And I need x transpose x. So this is p by n, this is n by p, this is p by p, symmetric. So I have p plus 1 divided by 2. And in y, I have n, and in x, I have np. So I have n 1 plus p. So I have n 1 plus p coefficients in this whole thing, and I have only, roughly p times p plus 1 divided by 2 coefficients. This is what we call sufficient statistics. So if I have a Gaussian distribution, you don't need, if you do like big data and all that. Sufficient statistics is solving big data problem 100 years ago. Have big data problem. You have a Gaussian distribution. Fine. Don't give me a vector of y's with 1,000,000 observations. Just give me y transpose y, x transpose y, x transpose x. Store this in a machine, and I can use it. If I change this Gaussianity here to a student, I'm screwed. So sufficient statistics is sufficient for a particular model. Okay. So why am I spending my few minutes with that? Well, because there is another thing I can do, taking advantage of those sufficient statistics. I can pre-compute a bunch of things to avoid recomputing those things in my MCMC scheme. And that's another thing, another lesson for people who are very familiar or not too familiar with MCMC scheme in Monte Carlo methods in general. In general, we have this feeling that, oh yeah, Monte Carlo solves everything. I can just run a bunch of simulations. Yes, in principle, but it's very costly. If you want to make the Monte Carlo error dropping from 0.1 to 0.01, you have to take the sample size in your MCMC from m to m squared. So if it's 1,000, you have to go to 1,000,000 to decrease one digit, because the variance of the Monte Carlo error goes, square root of n best. Anything you can do in closed form, analytically, you should do it, store it, use it. That will make your MCMC scheme, your Monte Carlo method in general, way much faster. So that's what we do. And the scheme becomes a little bit longer because now we have a loop for these subgroups of beta. But other than that, it's the same thing. Okay. And here's where this second bottleneck appears if you had just implemented a standard Gibbs sampler that we find in most packages. The full conditional for beta depends on that D, and I might have X transpose X, which is this quantity here on the board, but I'm always, at every single iteration, I'm always adding a diagonal matrix, and I need to invert that matrix. So if I do an MCMC, like a standard Gibbs sampler for this problem, in every single step of my MCMC, I have to do that inverse. While here, we already have all these inverses pre-computed, because when you look at these full conditionals, nowhere we will see X transpose X plus some quantity. So that was a very nice trick. I'm gonna skip this, and I want to show you like two examples, simulated examples of how our scheme compares to competing ones. One way for Bayesians or Monte Carlo users to compare schemes is by the effective sample size. So if you run your MCMC, suppose I run an MCMC and Lydia also runs her MCMC, and my MCMC is like a naive random walk metropolis, but it's very easy to compute, and I can run 1 million draws. But it has a very strong autocorrelation for the chains of the Markov chain Monte Carlo method. Hers takes more time to run each step, but has zero correlation. So how do I compare my method to her method? Well, definitely her method is better than mine, because mine has all this high autocorrelation. And that's what we call here is effective sample size. But the effective sample size, which is like a measure of how correlated the chains are, if the chains are not correlated, this quantity is 0, so the effective sample size is the actual sample size. If this variance is, let's say, this whole quantity is 1, then 1 plus 1, n will go to half of n. So the bigger the autocorrelation of the Markov chain, the smaller is the effective sample size. But I also have to take into account how much faster my MCMC is compared to yours. Maybe yours is much better, but it takes 1 hour for each iteration. Mine is horrible, but it takes 0.1 seconds. So I can run in 1 hour. When you run one step, I can run like a trillion draws. So that's why people not only consider effective sample size, but we consider effective sample size of your MCMC scheme per second. So you make a relative measure of how fast your scheme is in each second. So this is what people normally use these days. Okay. So this is what there'll be like a few slides here to finish the presentation, and that quantity is what we're going to use to compare methods. So simulation exercise. I'm going to focus on one, and then I'll show you the other one if I have time. Think about this. I simulate the matrix X as independent columns, IID Gaussian. Then I construct my Y's as a function of X. The usual simulation that anyone would do to simulate regression results given a particular value of beta. So now I'm going to use that to magnify it again, because that's what I'm going to finish anyway. So I want you to concentrate on that both column. Here we have our method, the slice scheme, with all these tricks that we described over the last 1 hour almost. Then we have, for instance, the Gibbs sampler here for this particular prime. There is already a Gibbs sampler implemented, so we compare to that Gibbs sampler. So you see that our method has effective sample size per second that is almost 3 times as good as this Gibbs sampler. And it's twice as good as this other method that someone else implemented in this R package mono MVN, which samples from a multivariate Gaussian, like a regression. When I change the priors, and these changes are only to show you that in our package, and I'll explain this package in a minute, is our R package, you can change all these priors and you're going to get results that are consistently better than these guys here. The effective sample size when the number of regressors is 1,000 it's smaller than the sample size, the actual sample size, but it's still much better than the competitor. Like you see, like that goes from 2,000 draws to, from 5,000 draws to 5. So you think you have 5,000 draws from that algorithm, but you only have 5. So it's very highly correlated. So I think let me show, I have another example here. Yeah. So in this example, in this other exercise, we were playing with the case where P is much larger than N. P, the number of regressors, N, the number of observations. For instance, in the first row, we have P regressors, 1,000, but we only have 300 observations. So when we do compare our method, which is this slice, with this method here that was proposed by John Drow in Ornstein in 2017, you see that our results are very comparable to his results. And if you compare ours to theirs, we are always like either winning or very close to them. Apart from this case here, which is where they beat us relatively badly. So you have only 100 observations and 3,000 regressors. So we have to study that particular case a bit more. But consistently, as you vary P, the number of regressors from 1,000, 1,500 to 3,000, and the number of observations increase from 300 to 600, 900, sometimes 450, 900, and 450 and 450. And you see that what we are proposing, which is based on a unique method, performs very well compared to the best existing alternative. Okay? So in the last minute, I only want to show the size. I will skip this. I just want to show so there's these slides are available on my web page next to the paper with the same title. So slides right there. I just wanted to show you. It's so small. I just wanted to show you a little bit of code, how easy it is to do this in R. So I'm going to magnify this, not much. So you can just install the package base-lm library. So this little bit here is because I simulated data according to this specification. So you have these slides there. You can go home and implement it. Then I feed OLS, very simple, right here, like lm of y tilde x minus 1, because x has a column of 1s. And then the Bayesian regularization is what I call here fit 1, fit 2, and fit 3. I use the same function base ln with y, comma, x, prior horseshoe, prior Laplace, prior reach. 10,000 draws, burn in 2,000. So run for 2,000, throw it away, and keep the following 8,000. Just one line. Everything else is in the default setting, and you can study this package in our paper. So if you run this code for this kind of simulation that I present here, you're going to get a table that looks like this with the true values, the OLS estimates for 20 coefficients, and what would be the estimates for each one of those other 3 methods. So with that, I think I'll finish. But remember, this was not a paper about statistical modeling. It was a paper about finding through statistical results better iterative schemes for posterior inference in a particular class of models that is very popular. So if that class becomes less popular, all of these become also less popular. And there is nothing wrong with that, because we already got this in the Journal of the Computation and Graphical Statistics, so it's the top journal in the area. So we are pretty proud of that. Thank you.
Okay. Thank you, Hedibert, for your presentation. We have time for a couple quick questions.
First, thank you for the excellent work and excellent presentation. I am just reminded how fortunate any student in your class must be to be learning from you. So I have kind of I'm not sure really, the answer may be it doesn't apply, but I've been sitting through a lot of talks lately on functional regression, so spline regression, and because we have a new colleague that is his area, and so he's been bringing a lot of people through. And it seems to me that everything that you've done would apply to functional regression from a spline perspective,
Yes,
assuming
that's a good point.
you keep the Gaussian structure.
Because in the spline or wavelet, whatever, as long as you keep the basis functions well defined, you can pre-construct them, and then they are the axis.
And then everything
That's
would follow
a
through.
very good point, because I gave this talk for like this is the third or fourth time, but I think this is the one that we should profit from, because then you can bring a bunch of nonlinear mean functions. It would still be linear through a very large set of coefficients, which is also very nice, because you can make that even much bigger, and then you'll be shrunk to zero when the coefficients are close to zero. Thank you. Yeah, that's a great example. We haven't implemented, but I will tell them. I'm just going to go and simulate some data from a spline setup and then see what happens. Thank you. Yeah, very good. What's your name?
My name is David. I'm from São João del Rei.
Okay.
Thank you for your presentation. Your work is very elegant.
Thank
I'm
you.
amazed by it.
Thanks to my two co-authors.
Yeah, of course. But my question is, when you compare the rank efficient case, your method with the other two authors in 2017.
This one.
Yes. I'm not familiar with their work, but I believe they aren't using an arbitrary prior, right? They have fixed priors.
So, good question. I don't know. That's where my co-authors will know much better than I am. I do think that they are doing for a very specific prior.
So
And then we mimic that one prior, and then compare to that. So,
but even when
but I'm not sure. So I have to go back and look at that and to be able to answer you properly.
But if that's the case, your method is even when you lose, you win.
Yes.
Right?
It's more robust in the sense that if I
Yeah.
change the prior, I can still use it, then maybe they can. But if they do, then at least our method is comparable to their method in most cases. We lose there, and then we make sure to include that in the paper just to keep that open for whoever wants to pursue that, even ourselves, but at some time in the future. But yeah, good point. I will, during the next session, I'm going to go to the paper and check it, and I'll let you know before the end of the meeting.
Okay, thank you.
Okay, more questions in the lunch or coffee break times. Let's say it again. Thank you.
Thank you.
Hedibert.